Here we're going to look at applying the Clapeyron equation to solid-liquid equilibrium in a similar manner that we apply it to vapor-liquid equilibrium. In this case, we're given heat of fusion, the energy to convert ice to water, and giving densities the solid and liquid phases. And what we want to calculate is the melting temperature when we're at this relatively high pressure. So the equation, the Clapeyron equation that would apply for solid-liquid equilibrium would have delta H of fusion, absolute temperature, and volume of the liquid minus volume of the solid. What I'm going to do is convert, to make sure our units are consistent, convert the values for heat of fusion and densities. So what I'm going to do is convert the heat of fusion units to a molar basis. I'm going to convert densities to specific volumes and also make them a molar basis. So I'm going to just write this down and pause while I do so. So here's the heat of fusion in molar units. The volume of liquid would be the molecular weight over the mass density. I'll make these substitutions. So there's a molar volume for liquid. I'll do the same thing for the solid. So now I can substitute these values into the Clapeyron equation. Now I want to make sure to have consistent units for pressure, so I'm going to do a units conversion. 1 megapascal cubic centimeter turns out to be equal to 1 joule. So therefore joules, cubic centimeters, and I'm going to have megapascals unit, which of course corresponds to pressure on the left side, and I'm going to have a temperature term which corresponds to temperature on the left side, so the units are consistent. Now let me rearrange the equation. So should be a little careful here. This is a minus sign because this term denominator is negative. Now let me rearrange this equation, and now I'll integrate both sides from pressure 1 to pressure 2, from temperature 1 to temperature 2. Left side is just P2 minus P1. The right side is the log of T2 over T1. So let's create a little more space here. And so T1, 273 Kelvin for pressure 1 of 100 kilopascals, which is 0.1 megapascals. Since we converted to units pressure megapascals up here. And temperature 2 is what we're solving for, and pressure 2 is 110 megapascals. So I'm just make the substitution of these numbers. Both pressures are megapascals. Of course, we have to use absolute temperature in these equations. Do this subtraction and rearrange. So the left side, when I do the division, 0.0304, right side hasn't changed. Let me take the exponents of both sides. So this is 970, and the right side T2 or 273, which means T2 is 264.8, which I'm going to call, based on significant figures, 265 Kelvin. So we lowered the temperature for melting by 8 degrees for a really very high pressure, 110 megapascals.